Dear friend, I am glad to greet you to the annual International Conference Algebraic Geometric Method of Analysis. We have been running it for 17 years. This year, we represent by 21 countries, and we will hear to more than 19 reports. The results of such a long work is the journal Proceedings of the International Geometry Center, which is included for indexing in the scientometric database Scopus, and is also included in category A of the list of scientific professional edition of Ukraine. We will be glad if you will provide the results of your research in our journal. All our achievements are possible with the support of Odessa National Academy of Food Technologies, Institute of Mathematics of Ukraine, and Kiev National University named after Taras Shevchenko. I would like to introduce the administration of our academy to you. The Director of Odessa National Academy of Food Technologies, Professor Bogdan Yegolov, Vice Rector for Scientific Work, Natalia Povrova, and Director of the Education Scientific Institute of Computer System and Technology Industry 4.0, Sergei Kotlik. I would like ask Sergei Kotlik say a few words to our participants.
Доброго дня. К сожалению, я не готовился к речи, но я приветствую всех участников нашей конференции, причем она уже достаточно традиционная конференция. Основателем, мы уже слышали, основателем этой конференции являются достаточно такие важные организации, МОН, Институт математики, ну и так далее. Эта конференция достаточно емкая по своему содержанию, так как все направления, в которых будут проведены доклады и в которых, наверное, будут опубликованы в журнале материалы, они относятся к различным видам геометрии, методам анализа, общей алгебраичной топологии и так далее, и так далее, и так далее. Заседания этой конференции всегда отличались научностью, всегда отличались новизной. Поэтому от имени Навчально-наукового института компьютерной системы технологий индустрии 4.0 нашей академии я приветствую участников конференции и всех, кто помогал в ее создании. Всем плідної роботи на нашей конференции.
Спасибо. Александр Легот.
Мне слово?
Да.
Okay, dear participant, I am glad to welcome you to our annual conference. I am happy that this conference is dedicated to Yuri Yuryevich Trahimchuk, the scientific advisor of my scientific advisor, thus my scientific grandfather. I am very pleased that thanks to expansion of the topics and COVID, so many scientists have joined us. I would like to thank my colleagues Nadia Konovenko, Yulia Peshchenko, and Sergei Maximenko for their organizational work in holding the conference and publishing our journal. And I am pleased to introduce our first speaker, Anatoly Golberg. So, Anatoly, please, you can speak.
Thank you very much. Let me only share screen. Just a moment. Okay. Do you see
Yes.
My presentation? Yes. Thank you very much. I'm going to prepare my watch. Okay. First of all, I would like to thank the organizers for inviting me to participate in this great event and the possibility to present talk. it is really great that although the conference was planned to be held a year ago and was postponed due to the well-known reasons, the COVID pandemic, now it can be held in online form and dedicated to outstanding mathematician and prominent person, Yuri Yurievich Trokhinchuk. The main topic of my talk relates to one of approaches in multidimensional mapping theory. There are three main approaches: analytic, geometric, modulus, and the metric one. In this talk, we will discuss the connection between various classes of mappings which rely purely on metric approach, namely classes of mappings of finite metric distortion, finitely by Lipschitz, quasi-symmetric, and metrically quasi-conformal mappings. But we discuss also the connection between FFD homeomorphisms and class of mappings whose definition based on metric approach. I mean lower Q homeomorphism. And we will, as an application, we will provide some sufficient condition for boundary correspondence between such mappings on Riemannian manifolds. And we intend to illustrate some of them by examples of mappings of finite metric distortion. This talk is based on our joint works with Elena Afanasieva Institute of Applied Mathematics and Mechanics, Slaviansk, Ukraine. And it is important to mention, in my opinion, that in some sense, our approach goes back to the so-called Borg-Bischoff-Trokhinchuk theory on analyticity. I will explain a little bit later more precisely. The idea is following. In 1937, Bischoff generalized the Borg theorem on analytic function, and this condition, which is purely metric, you can see here the maximal distances over minimal distances, implies analyticity of function, of course, as this quantity tends to 1. And also, I would like to say that a great contribution to this theory was done by Yuri Yurievich Trokhinchuk by extending from univalence mapping to continuous mappings. And in some sense, all the topics in our talk can be connected this the mentioned theory. I personally very proud that I knew Yuri Yurievich and we met in Kiev Institute of Mathematics many times, and the last possibility to communicate to him was about 4 years ago. It was my last visit to Kiev in the beginning of July 2017, and the person who arranged this talk to Yuri Yurievich by phone was a former student of Yuri Yurievich, Yuri Borisovich Zelensky. Unfortunately, he passed away in a couple of weeks at the same month. It is well known that Yuri Yurievich results are absolutely classical. Let me start this well-known Cauchy theorem, which means that if a continuous function is continuous and monogenic in a domain D, that it is analytic in this domain. Let me recall that homogeneity means the existence of complex derivatives. It is necessary to know that this result in such a form is due to Gursa, since in the Cauchy theorem there's one more restriction. He proved this theorem under continuity of the derivatives, and in about 70 years, Goursat succeeded to remove this additional requirement, and the works by Goursat stimulated many mathematicians to find the condition as soon as weak as possible for analyticity of function. It is clear even at the level of undergraduate course in complex functions that existence of such limit is equivalent to existence of both limits. The first one can be characterized as independence of stretching in the given direction, and the second is preservation of angles at the points where the derivative does not vanish. And Bohr in 1918 proved the following result, applying only this limit, and he proved that if this limit exists and differs from 0 at every point of a domain D, that either function f or its conjugate is analytic in the domain. You can see in the Bohr theorem, this assumption, univariance of mappings, is essential, since the Bohr example shows that this condition, univariance, cannot be removed. Otherwise, the theorem is false. Next extension of this theorem, and it is easy to see that this condition is weaker than existence of this limit, was given by Menshov in 1937, and this property, you can see, has absolutely metric approach, as I mentioned at the beginning of the talk. And this property, if such quantity tends to 0 as R tends to 1, and tends to 1 as R, this quantity, this limit is equal to 1 as R tends to 0, then this property can be treated as preservation of infinitesimal circles. And this property also implies analyticity of functions. Here C is a circle centered at the node with radius R, which lies in the domain. And the same conclusion, either F or its conjugate is analytic in D. Also here, univariance is essential condition, and the contribution given by Yuri Yurevich was based on his theory of sets of homogeneity. Also, he considered, instead of univariant mappings, inter mappings, and extended the property of preservation, sense preserving, to orientation preserving at viewpoint. Here I can refer to his monograph of in Russian in 1963, and this monograph was translated to English in the next year. And now this theorem implies analyticity for continuous function. You can see this the constant stretching. It is generalization of Bohr theorem, and you can see also the generalization of this generalization of the Minshev theorem, this the same quantity which will appear throughout all our talk. So we will discuss various properties of mappings, regularity properties, of course, mappings which rely on purely metric approach, namely homeomorphism of finite metric distortion and Lipschitz and bi-Lipschitz mapping, finitely Lipschitz and bi-Lipschitz mappings, quasi-symmetric and quasi-conformal mappings in the metric sense. All our result will be given on Riemannian manifolds, and by Riemannian manifolds we mean n-dimensional differential connected manifold with a Riemannian metric. Lipschitzness. It means that there exists absolute constant L such that the image in the image is restricted from above by a product of this constant L and the distance in pre-image for any points x and y from in the manifold. And by Lipschitz, mapping is characterized by this double inequality. Here we have to add the left-hand side that also it is restricted from below by this product 1 over L times D, and clear that L is greater than or equal to 1, and for 1 the mapping becomes an isometry. And we consider essentially by the class of mappings, which is classes of mappings, which are called finitely Lipschitz. It means that now this condition is replaced by the following, and you can see that the meaning of this guy is maximal stretching, or it is also can be called maximal derivative of mapping f at point x. You can see here the limb sub, and this limb sub should be only finite for all points x in D. And to define finitely by Lipschitz, we have to add this part of this inequality, and here small l is limb inf of the same ratio. And the following example can illustrate how this class is. These classes are wider than standard Lipschitz and by Lipschitz. And by the way, I would like to refer to the monograph by Martio Rezanov Srebra Yakubov of 2009 on various properties of such mappings in Euclidean spaces and also in metric spaces. And now let me show the following example in Rn. Let our mapping is defined by the following formula. There P lies between 1 and n-1, and our mapping is defined in the unbounded cylinder. This is the cross product of n-1 dimensional unit ball and unbounded interval 1 infinity. By a direct calculation, it is not hard to get the following results, that the capital L is equal to this quantity. It is easy to see that this quantity is finite in the whole cylinder, but it can not be bounded from above, and the small l is equal to 1 over xn, and also this quantity cannot be separated from 0 by any constant. It is possible, but cannot be separated from 0 by any constant. We will use we have to require that the image, the manifold in image, should be hyperconvex. This is the definition of hyperconvexity, and this notion is due to Anandjan and Panic-Pagdi is due to 1956, and who proved that hyperconvex space in non-expansive retract of any metric space in which it is isometrically embedded. Two classical examples can describe this quasi-convexity. First of all, it is the real line, and the second example is Euclidean spaces with infinity distances. And our first result says, if we consider finitely Lipschitz homeomorphism and omega be an open set in a Riemannian manifold M, and we have to suppose that M prime is a hyperconvex space, and K is integer between 1 and n, an integer between 1 and n, that any set of k-dimensional zero measure is mapped onto the set of zero, the same measure, I mean zero measure, and vice versa. This property is very important for change variable formulas, and it is called in this direction. It is called the losing n property, and in opposite direction, the n-1 losing property. And even from the theory, elasticity theory, it has a very interesting presentation. If we consider as a transformation of a solid body to another solid body, so no material can be created from nothing. And the next corollary of this theorem says, now if we consider a finitely Lipschitz homeomorphism, the additional condition that small l is positive for all points, first of all, it immediately implies that we have finitely by Lipschitz mappings, and of course this mapping possesses the losing n and n-1 property. Let me only say that this respect to hyperconvexity, this condition allows us to use Kilsbraun type theorems on Lipschitz extension. Next class of mappings is characterized by the following metric description. Let eta be a real valued homeomorphism, a homeomorphism from domain D to domain D prime is called eta quasi-symmetric if this inequality holds. You can see here the ratio between two distances in the pre-image, and here the ratio of distance at the same point, in the image, and here in the pre-image for any triple points x, y, z. There are x, of course, should be different. X should be different from z. Let me note that first of all, what is the difference between Lipschitz mappings and quasi-symmetric mappings? First of all, quasi-symmetry involves 3 points point condition instead of 2, 1. The Lipschitz mappings distort absolute distances by a bounded amount. Roughly speaking, by Lipschitz mappings distort both shape and size, the shape and the size of an object by a bounded account, while the quasi-symmetry preserves only the approximate shape. And one more class, a little bit weaker class of quasi-symmetric mappings is weakly H quasi-symmetric mapping. There, this ratio is restricted from above by a product of absolute constant H and this ratio. Only let me, first of all, I would like here to refer to a monograph by Riemannian, lectures on metric spaces. And in general, weakly H quasi-symmetric mapping need not to be eta quasi-symmetric, but if we apply, and next we consider the relation between the above classes of mappings and quasi-conformal mappings, which will be defined metrically, and we will use this property C quasi-convex. It means there exists a constant C such that every pair of points X and Y can be joined by a curve whose length does not exceed this product C times the distance. Of course, we can reduce this property to a domain, first to locally quasi-convexity and then to a domain. And here also I would like to refer to papers by Riemannian and also Gering-Marteau. The theorem 2 says that if both our domains of Riemannian manifolds and prime are C quasi-convex, in this case, eta quasi-symmetry and weak H quasi-symmetry are equivalent. This is the relation between by Lipschitz homomorphism and by Lipschitz, I mean this constant in this definition, in this double inequality. So weakly H quasi-symmetry homomorphism, every L by Lipschitz homomorphism is also a weakly H quasi-symmetric homomorphism. This H, which is equal to L squared. So it is quantitative. You see, almost the same guy as was in the theorems by Menshov and Trachimchuk, and we say that homomorphism is called metrically K quasi-conformal. Is there is a constant K, finite constant K, such that the lim sub of this quantity is restricted from above by K for all points X. Theorem 4 shows that any K quasi-conformal mappings, in view of our definition, is locally a weakly H quasi-symmetric indeed. And here let me note that locally here is essential in this theorem in a global form fails to be quantitative, and we can show the following example, which was suggested by Pekka Koskela. And if we consider as Riemannian manifolds the Riemann spheres without the north pole, And we consider a Möbius transformation. And a Möbius transformation is conformal mapping, or K quasi-conformal, this K is equal to 1, of lower half of this sphere onto sphere without small cap in the north. So in this case, this constant H can be bigger as possible. And so this theorem really only this theorem only is true only in the local form. Next, theorem 5 says any L by Lipschitz homeomorphism is K quasi-conformal mapping in the same domain. Two more conditions. First, it's Poincare inequality implies quasi-convexity, and also QED condition also implies quasi-convexity. Let me say 2 words on Poincare inequality. First of all, what is upper gradient? Upper gradient here is a Borel function from x to real valued function from x to the segment 0 infinity, and it is clear that this inequality holds if a function u is a smooth function in on or n or any Riemannian manifolds, and row here, any row which satisfies this inequality is called upper gradient. It is clear that upper gradient is not unique, or for example, if we consider row which is identically equal to infinity, this inequality holds. And Poincare inequality is the following. It is a weak 1p Poincare inequality. Here the real parameter p, and weak, why? Since in the left-hand side we consider a smaller ball than in the this average in the right-hand side. If here and here we consider the same ball, this Poincare inequality, this inequality is called 1p Poincare inequality, and since this condition implies quasi-convexity, we can reformulate our theorem, replacing the quasi-convexity by satisfying 1p Poincare inequality for such p, and we obtain the same results, namely the equivalence of weakly quasi-symmetry and big quasi-symmetry and eta quasi-symmetry, then relation that every Lipschitz by Lipschitz homeomorphism is eta is H quasi-symmetry, weak H quasi-symmetry. Also, the relation between K quasi-conformality and H quasi-symmetry, and the last theorem. Also, what is QED domain? This means of quasi-extremal distances. Here we use the notion of model of families of curves. In a couple of slides, I will define the modulus, or model. It is sometimes it is called modulus, sometimes module. I will define explicitly here. Delta of A, B, C means the family of all curves which join the sets A and B in C. A and B here should be assumed to lie in the closure of C. And QED condition means the following. Here in the left-hand side, we consider the family of all curves which join the continuum A and F in the manifold, and in right-hand side, we consider only we consider a subfamily of this family of curves which lie in the domain D. So if the modulus can be restricted by constant C times the modulus in the of this family, the domain is called of quasi-extremal distances, and the same results are true also for QED domains. I mean, for results mentioned above for quasi-convex domains and for domains for which satisfy Poincare inequality. Next class of mappings also has the following presentation, definitely metric presentation. We consider the same condition like in finitely by Lipschitz homeomorphisms, but now we require that these conditions should hold almost everywhere, and in addition, our mapping should satisfy the losing property with respect to n-dimensional Hausdorff measure. Let me recall that it carries out every set of zero n-dimensional Hausdorff measure onto a set of the same zero measure. And using theorem 1, we obtain the following. If we assume that M prime is hyperconvex space, that every finitely by Lipschitz homeomorphism is homeomorphism of finite metric distortion. Abbreviation is following. And theorem 6 says that also every by Lipschitz, in the regular, in the standard sense, it is clear since every by Lipschitz homeomorphism is also finitely by Lipschitz homeomorphism. Now we already arrived to the definition of modulus of family gamma. First of all, we have to define what is admissibility condition. Admissibility condition for a family of k-dimensional surfaces, family gamma of surfaces S in manifold. K is integer between 1 and n-1, says that such weighted surface integral should be separated from 0. So we mean such integral should be greater than or equal to 1 for any surface from our family. It is clear why, because in the modulus of family, we consider the infimum of such Borel measurable functions, non-negative measurable function, to the power n. To define the class of lower Q homeomorphism, they have to become this admissibility condition. So we consider also class of extensively admissible. And here I would like again to refer to monograph by Marty Rezanov, the Kubo moduli in mapping theory. And extensively admissible means that now this condition holds for almost all surfaces, in which sense almost all, except for subfamily whose modulus vanishes. This is the definition of lower Q homeomorphism. First of all, why lower? Here, the modulus of this image of family sigma epsilon. I will show what is sigma epsilon, is restricted from below by such integral. Such integral depends on measurable function, a priori defined measurable function q, and rho here is extensively admissible, and infimum is taken over all such. If we replace q by a constant k, we obtain the left-hand side of the well-known property for k quasi-conformal mappings, which is called quasi-invariance of quasi-conformal mappings. It means that the modulus can be changed up to a constant factor k, and sigma epsilon is the family of geodesic spheres of radius epsilon, and the image of this of modulus of this family, the modulus of the image should be restricted from below by such integral. And let me only show it is the we can say not whole spheres. It is pieces of spheres which lie in our domain. Moreover, the point x naught can be a boundary point of and our one of our main results says that FMD homomorphism satisfying n property with respect to n-1 Hausdorff measure is lower Q homomorphism. The Q is the outer dilatation. Outer dilatation means the following. You can see here at the point there, this guy does not vanish, and it is generalized Jacobian or volume derivatives, and this quantity exists almost everywhere, and this is the same maximal station to the power n over this generalized Jacobian, and we can extend for if L vanishes by 1 and infinity other size. This is also corollary of this theorem with respect to by Lipschitz homomorphisms. And I would like to present probably not more than two results regarding to boundary correspondence, and our idea was to illustrate such a result by some mappings of punctured unit ball in Rn, and the first one is following. It has unremovable singularity at the origin, and the image of this punctured ball is the spherical ring with radii 1 and 2, and by direct calculation we obtain the following results, and it is easy to see that this mapping is of finite metric distortion. Next, this mapping has removed singularity at the origin. Also, it is FMO homomorphism, and two more homomorphism. This is a classical example of quasi-conformal mapping. Here also, since alpha lies between 0 and 1, it also has a removable singularity at the origin, and this is a result. By the way, here L is restricted from above, but small l is cannot be separated from 0 by any constant. And the last example, it is kind of a rotation in the plane x1, x2. This mapping is identity with respect to coordinates x3, xn, and and the rotation here with the angle which depends on x1, x2, and the rotation is quite quick as x1, x2 tend to 0. Of course, to give some boundary results, we have to provide some restrictions on the boundary. We will consider both two conditions, weakly flat, and weakly flat is, for instance, extension of P1 property by Wechsler. Here, let us refer to the monograph by Wechsler, lectures on n-dimensional quasi-conformal mappings. And the definition of this quantity is not so easy for public, which is not so familiar with this. Let me explain in the following example. Here we consider the family of curves which join two continua, and the boundary here consists of the, let us say that we are in R2 of these closed curves and this segment, and x0 is not in at point x0, the boundary is not weakly flat. Why? Because due to the properties of the modulus, this quantity is restricted from above by a constant. And in this definition, it is assumed that it can be bigger than any real number, positive real number p. And one more condition, strongly accessible. If strongly accessible at point x, it is a weaker condition. And also let me illustrate by example in which the point is not strongly accessible. It is like two combs, this teeth, which where here distances approach to 0, and it is possible to connect this such point by only non-rectifiable curve. And in this case, but non-rectifiable curves, it is well known, the modulus of non-rectifiable, of the family of non-rectifiable curves is equal to 0. And we obtain some results. Now I will stop in and we obtain the results on continuous and homomorphic extension for the mappings on it inverse, and it can be illustrated by our examples. And first example, for example, shows that this theorem is holds since the outer dilatation belongs to this class. And the second example shows that this is really only sufficient condition, since in this case the mapping does not satisfy the following condition, although the continuous extension holds. And in the theorem 2, we show that such condition, the divergence of such integral, is not only sufficient in some sense, it is also necessary. I see that my time is over, and I would like to thank once again the organizer for inviting me to give a talk. And I would like to wish to all of us, first of all, good length, and to pass as soon as possible the COVID pandemic and come back to regular conferences, regular conversations, and collaborations. Thank you very much.
Thank you. Let's thank